Alright, what's going on, folks? Mr. Brunsvold here. Alright, so right now we're going to take some notes on orbital diagrams. So go ahead and get the orbital diagrams, notes, examples, and practice open in Notability. As you watch this video lesson, take notes, follow along with the examples, and then try to complete the practice problems. And then you can submit the assignment to Schoology. Okay, so what is an orbital? An orbital is a space outside the nucleus where an electron can be found. Right, up until now, we've been drawing them like this. Right, it's like little circles outside. The electrons almost look like little planets orbiting around the protons and neutrons, which are kind of like the sun. At this point, we're going to start using a little bit different model to talk about the atoms. We're going to start using what's known as the Schrodinger Model, and we're going to start talking about the electron orbitals a little bit different. So what you really need to realize is that atoms are three-dimensional, and so you can really think of, so imagine the nucleus at the center here, you can really think of your first orbital as like a sphere, right? So the electrons, they sort of exist on the surface of this sphere, and they buzz around the outside. Okay? When the orbital is shaped like a sphere, we call it an s orbital. And so the first thing you're going to label on that periodic table on your notes is the s block. And that's for those spherical shaped orbitals. And so all of these elements, helium down through francium, beryllium through radium, and helium, they're valence electrons. Remember, valence means the outermost electrons. They exist on that sphere. Okay, let's keep going with the video. Okay, so the next type of orbital is called a P-shaped orbital. You can see it kind of looks like maybe like a dumbbell, or maybe like two balloons, like end to end. And so for the P-shaped orbital, again, the electron exists sort of like on the surface of this. So not on the inside, but just on the edge. And again, it's three-dimensional. Okay, and so these are the atoms whose valence electrons exist on the p block, or exist in a p orbital. So we call this the p block. Okay, so then let's just keep going. And so then those numbers that are out front there, the 2s, those tell you which period on the periodic table you have to look to find them. So for example, right now they're showing 2p. So what they're talking about is in the second period, the second row. So the elements that would have electrons in the 2p orbital would be like boron, carbon, nitrogen, oxygen, fluorine, neon, because they're in the second row, but they're in the p block. So earlier they were talking about 2s, that would be lithium and beryllium. Right? Lithium and beryllium are in the s block, and they're in the second row. Before that they were talking about 1s, so that would be hydrogen and helium, because they're in the first row, and they're in the s block. Okay, so then let's keep going. So now we're up to 3s. Now our 3p orbitals. Keep in mind, you're not going to be required to draw these. That'll be in chemistry when you have to know how to draw these. For this class, you mostly just need to know their names. Right. Then after 3p is going to come 4s. Pretty straightforward up to this point. Now things are going to get a little bit weird. So after the s orbital starts coming the d orbitals. And we're going to see d orbitals sort of have all different shapes. So that one looked kind of like p orbital with a ring around it. That one looks like sort of like 2p orbitals. This one also kind of looks like two sets of p orbitals. Same thing with that one. Also has like two sets of p orbitals. And same thing with this last one. Looks like two sets of p orbitals, but they're all sorts of like different orientations. You can see once they get all on top of each other, it's kind of difficult to even keep them straight. Okay, and so this is the D block right here. It's going to be from scandium to zinc, from yttrium to cadmium, from hafnium to mercury, from rutherfordium to copernicum, and then lutetium and lawrencium. Okay, and then there's also an F block. That's going to be these ones down here. You can Google it if you want to see what the F block looks like. To be honest, it really doesn't matter because you're not going to do any chemistry with these ones down here anyways. How do I know that? Well, let me put it to you this way. I went through 5 years of undergraduate in college, and I never did any chemistry with any of these in there. So I very much doubt that you're going to do any chemistry with them in high school. Okay, so orbital diagrams. Maps, and later I'll show you what they all look like together. I'm not sure why I didn't put that in right there. So what is an orbital diagram? An orbital diagram is a map for the orbitals that the electrons will occupy. And we're going to learn how to draw them today. We're going to fill in orbitals following these three rules. So first off is the Aufbau principle. Electrons will occupy the lowest energy orbital first. So you kind of see 1s is the first orbital that gets occupied, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s. So really we're just following the arrows to see which orbitals get filled in first here. So what I would write on your notes is underneath Aufbau principle, write electrons will occupy the lowest energy orbital first. And then next to this little chart on the next page, write Aufbau principle. Next up is Hund's rule. Hund's rule says that electrons will occupy separate suborbitals if there is enough space. So go ahead and write that down underneath Hund's rule. And then you can show this little chart right here with 3 electrons. And so the point is none of these electrons are paired up. So we could have put these 2 electrons in the same box, and we'll show what that looks like later. But if there's room, they would much rather occupy separate boxes. Next up is the Pauli exclusion principle. When electrons occupy the same orbital, they have opposite spin. So now I'm going to show you when there's just one box, a lot of times you'll end up with 2 electrons in that box. And we always draw 1 electron pointed up and 1 electron pointed down to show that they're spinning. I don't know if you knew this, but electrons have spin. And we draw 1 up and 1 down to show that they have opposite spins. So one you might think is like spinning clockwise and the other one's spinning counterclockwise. Or if you play tennis, you might think 1 electron has top spin and 1 electron has back spin. Okay, so let's go through a few examples. We're going to identify these elements. So this is sort of how we write our orbital diagrams. We always say which orbital it is at the top. So this is the 1s orbital, this is the 2s orbital, this is the 2p orbital. And then this is how they're occupied. So this 1s orbital has 2 electrons, and then the 2s orbital has 1 electron. You can always tell which element it is by the valence, right? So you just look at the highest occupied orbital. That would be this one. So 2s. So we want to look, where would the 2s only have 1 electron? So this is the fully filled in chart. So if you didn't get it all filled out, this is what it should look like. We're going to look in the S block, in the 2S block, so 2 is the second row. We're going to look for 2S1, so what's the first element in the S block? That's lithium. So this is the orbital diagram for lithium. Well, what if there was 2 electrons in the S block? So then 1, 2, that would get us to beryllium. All right, next we're going to look in the 2p block for something with 1 electron. So again, we're in the second row, but now we got to go over to the p block. The first element in there is aluminum. So aluminum is, whoops, let's try that again. Sorry, we're in the second row. The first element in there is boron. And so this one is boron. So now we'll look at for the second element in the 2p block. So that's right here, carbon, right? Row 2, 1, 2. So that's carbon. The third element right here is nitrogen. The fourth element right here is oxygen. The fifth element right here is fluorine. And the sixth element right here is neon. Okay, let's do some expert examples. So this one, we're going to look all the way over here. Okay, 3D. All right, this doesn't seem that complicated. I'm just going to look at the periodic table for the D block. And I'm going to look in the third period. So as I follow over to the third period, well, wait, there's no D block in the third period. The D block starts in the fourth period. So which elements do I look at? Well, the D block is a little bit screwy. So I just kind of cut it out so that we're just looking at the D block. This row right here is 3D. This row right here is 4D. This row right here and lutetium down at the bottom, that's 5D. And then this row right here and lawrencium down at the bottom are 6D. Why is the D block off by one number, right? Because this should really be the fourth row. Well, it's kind of tough to explain. It has to do with quantum mechanics. We're not going to get into it in this course. Just make sure that you know for the D block that this is 3D, this one's 4D, this one's 5D, and this one's 6D. So, if we take a look at our element, this is the 3D block, and it's the third element in the 3D block because we have 3 electrons in here. So I'm going to count over. 1, 2, 3. That should get us to vanadium. So this is vanadium. Okay, sorry, I forgot what I was going to tell you on this one. There is a shortened way to write this. So if you look at vanadium, 1s, 2s, 2p, 3s, 3p, you can see I kind of did all those in a different color. Well, if you look for 3p all the way filled, all 6 electrons filled, so row 3, P block, 1, 2, 3, 4, 5, 6. That's argon. That's a noble gas. So a shortened way to write, so here's the orbital diagram for argon. A shortened way to write the orbital diagram for vanadium is just to take this front part that I've written in red, give the noble gas for that, and then we just give the orbital diagram for the valence. So what do I mean by the valence? Well, if we look, vanadium's right here, so we're just giving the electrons that are in the fourth period here. We don't worry about the other electrons. For those, we just write argon, because argon is the closest noble gas to vanadium, or it's the noble gas that comes before vanadium. Okay, and so then when you do this assignment, I am at times going to ask you to identify and draw these orbitals in the abbreviated form. So when I say abbreviated, I mean I want you to write the nearest noble gas, so or the previous noble gas. So the previous noble gas for vanadium is argon, and then you just write out the electrons in the valence. So in the period for argon or for vanadium. So let's look through another example of that. So here, this one in the abbreviated form, it's xenon, and then 6s2 and 4f7. Right? Because there's 7 electrons here. So here's xenon, and then you hit 6s2, so that would be these two. Then we look at our lanthanoids, which are down here, and we're going to count to 7 in the F block. So 1, 2, 3, 4, 5, 6, 7. We'll end up at europium. And then you can label your F block 4F and 5F. Sorry, I forgot to mention that. Just kind of like the D block, the F block's a little bit screwy. But this one is 4F and this one's 5F. And it ends up being europium because that's the 7th element in the 4F block. So let's draw some orbital diagrams. First up is helium. Here's helium right here. It's the second one in the P block. So if you want to, you can think of helium as being right here, 1, 2. So we need to draw it a 1s orbital, and we're going to put 2 electrons in there. Next up, we're going to do silicon. Silicon is right here. So as we fill this one out, it's one S block here and here should be filled. And next up comes these two, right? Because those were elements 1 and 2. So then elements 3 and 4, those are in the 2s block. Those electrons should be filled. So we fill it in with 2 electrons. Remember, we draw 1 up and 1 down. Next up is going to be the P block. Now for the P block, you're going to draw 3 boxes. And that's because when you look across the P block, you should count 1, 2, 3, 4, 5, 6 elements. That means that the P block can hold 6 electrons. You can put 2 electrons in each box, so 6 divided by 2 is 3. And I put a little chart on your notes to show you how many blocks you should be drawing for, or how many squares you should be drawing for each kind of block. So for the P block, we're going to draw 3, and we're going to fill each one in with 2 electrons. So that's for the 2P. So next up comes 3s. So that's these two right here. Those should be filled. And then last up, we land on silicon, which is in the 3P block. So silicon is right here. It's the second element in the 3P block. So we're going to put 2 electrons in there. So again, the 3P block, I didn't write 3P down here, but that's okay. You can write 3P underneath here. Remember, whenever we're doing a P block, we need to do 3 boxes. And since it's silicon, we can fill in 1, 2 electrons. So 1, 2. We draw them going the same direction, and we don't put them in the same box together, because if you kind of think like back to the Hog Hilton, right? Imagine the electrons are like the pigs, right? They don't like sleeping next to each other if they don't have to. They would rather have their own room. Okay, so next up is manganese. Manganese is right here on the periodic table. For manganese, we're going to fill it in with the abbreviated. And so for that reason, we need to go back to the last noble gas. So as I follow back from manganese, the first noble gas that I hit is argon, every pirate's favorite element. Argon So that's going to be the first thing that we write down. And then up next, we can start taking a look at the valence electrons. So after argon, we hit, this is the first, second, third, fourth row. So this is the 4s block right here. So we're going to fill in 4s with 2 electrons. And then next up, we're going to take a look at the D block here. And so remember that this is the 3D block, and manganese is the first, second, third, fourth, fifth. And so we're going to fill it in with 5 electrons. 1, 2, 3, 4, 5. Don't pair them up at all. Remember, they're like pigs. They would rather have their own room if they can. Last up is terbium. Where is terbium? Terbium's right here. And so again, we're going to fill that in with noble gas configuration. So this is a little bit tricky to figure out which noble gas you should be using. So for this, I like using this periodic table because you can do the wide view. So here's terbium. Oh, except we can't fit the wide view in one screen. Maybe if I go full screen. And then if I zoom out. Okay, so this is terbium right here. But if we follow that over back, we can see that it's in the 6th period. So what's the noble gas in the 5th period? That's xenon. That's what we're going to start off with here, is xenon. And then next we're just going to look at the valency of terbium. So here's terbium right here. We can see that the 6s should be filled. So 6s is what you want to write down first. And that should be filled. And then next we'll fill in the F block for terbium. Remember that for the F block, this is the 4F block. And so we want to fill this in with 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Oh, this is not correct, right? Because as we count across, this is only 7 electrons. So Mr. Brunsvold made a little mistake right here. We should fill in 1 electron going down right here and another electron going down right here. So actually, let me do that real quick. Go to edit. What slide are we on? Like 60 or something like that. No, more than that. Oh, this is the last slide. Okay, so for this one, we should draw one more arrow going down right there, and one more arrow going down right there. And again, the reason why terbium is the 9th element, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need to fill in 9 electrons. So we fill in the first 7, and then here's 8 and 9 going down.